Greetings, tubes! Before you assemble your engine, the first matter of business is to see what kind of parts you've got. You can't just bolt new parts on and expect them all to fit. You have to spend a little bit of time to make sure you're not wasting more of your valuable time and hard-earned money. This is the last 10 pages of the factory service manual in practice. The result will be an installed rotating assembly, and while we're at it, I'll expand on techniques already covered in the blueprint series. The first thing you need to do is make sure the deck of the block is flat. The technique is simple, and I've covered it before in the Blueprint 108 video. The easy way to remember it is split it, box it, exit. I'm using a straight edge from a brand new carpenter square and a 2000ths feeler gauge. The limit is 4000ths for machining, but I'm good. Couldn't squeak a 2000ths through it anywhere. I tried. You saw it. It's flat. Next we're going to spec the crank. You have to do this to make sure the crank isn't junk. If it's been through too much work already, then you might have a hard time getting your bearing sizes right. The crank I'm going to be using is the same crank that was in my crankshaft refurbishing video. It was a stock 6-bolt version crank with 130,000 miles on it. I had it polished and chamfered to improve oil flow. I was lucky to have an extra one available for this project, that's for sure. Big thanks, Domestic Killer. The old one was dicked, but before we get into measuring anything, I need to clean all the oil and dust off the bearing surfaces from sitting for so long. First thing I want to remind everyone about is whenever you're cleaning parts for assembly, don't ever use these red rags or paper towels on engine surfaces unless you have a dry, high-pressure air source to blast the parts off thoroughly afterwards, and the patience to give them a thorough inspection. The fibers from these kinds of fabrics are fairly coarse, and they love to stick to stuff. If you get them between mating surfaces or on bearing journals, they'll mess up all of your measurements at the very least. These are a really nice set of old school Mitutoyo 10,000th micrometers. I don't deserve this, but I sure did need it. Big thanks, Chad. In order to ensure the accuracy of your measurements and prevent damaging parts, both the tools and the parts need to be spotlessly clean. You should have all your micrometers and parts at room temperature, or at least the same temperature. Verify or set the 0 point using a known good reference before you begin taking measurements, and make sure you have all of the 0 marks lined up. There's actually 2 of them on the 10,000th spot. The micrometers in my Blueprint 101 video are completely inadequate for engine assembly. They're great props to teach people with, and these read exactly like the ones I demonstrated, except they have an extra ring of numbers on the barrel that give you the 4th decimal place. You want the fit to be as snug as you can get it and still pass over the highest point on the journal. I've got 2.25 plus 18 thousandths, which is 2.243, and on the barrel I've got the marks lining up on the 6. So we've got 2.2436. It gets pretty repetitive from here on out. You need a 1 to 2 inch for the pins, a 2 to 3 inch for the mains, and a 3 to 4 inch for the pistons in order to spec out a 4G series engine. Once again, we have a 2.243 around the barrel, we've got a 7, so 2.2437. You see how this works? It works just like the other ones I showed you, just with 10 times greater accuracy. On the center main, I've got a 2.2435. That's the smallest one so far, but they're all really close. They're all hitting right around dead center spec, and I can't complain about that. I spoke too soon. Nah, that ain't bad. There's the biggest one at 2.2438. Before I had this polished, every journal was dead on spec, so it looks like polishing the crank took off about 4/10,000ths of an inch. Number 5 rings in at 2.2435, so there you have it. All of those mains are within factory spec. In theory, you should be taking 3 measurements on each journal to check for egg and taper. Now let's get measurements on the pins. Factory spec is 1.7709 to 1.7717. I'm using inch measurement micrometers, so those are the specs I'll be following. Once again, you zero the micrometer with your reference. Don't forget to make sure your reference and the micrometer are squeaky clean, or else 0 doesn't mean anything. And check all your marks again. We're using the 1 to 2 inch micrometer, so the 1 inch is a given. The process is still the same, so here we've got 750 thousandths plus 21, and it's lined up with the 1, so 1 inch, 7,711 10,000ths. And that's a mouthful. On number 2, we're a little tighter because we didn't quite cross the 21 line, and it looks like we've got a 7 on the barrel. Looks like we pulled off the 21 this time, so 1.771, and we're lined up on the 1. Last one looks like more of the same, came up short. Can we hit the loose end of spec? Yes sir, there's the 9, we pulled it off. Being 2/10,000ths of an inch loose on number 2 doesn't concern me in the least. I need to check to see if my bearings are the right size so I can put what I've got back together. Before I can do that, I have to clean every part, ensuring that it's bone dry with no foreign material on any surface. I could measure the main bores of the block with my dial bore gauge, but the factory service manual doesn't suggest doing any of that, and it really won't matter if I find it out of spec. I won't be doing any machine work on this block, so I'm going to check it the way the factory service manual says to check it. I bought standard 6-bolt ACL H series bearings, a considerable upgrade for this engine. There's 2 sets of bearings in this box. One is wrapped in yellow to alert you that they're different than the others. The yellow pack goes in the main caps. The other pack goes in the block. The reason behind this is based on the thrust loads and the oil holes. The bearings are packaged with a light coating of oil, and that has to go too. You want no liquids of any kind between the bearing and the block, or else you could unseat or even spin a bearing on the first startup when you hit the key. Oil on the backs of the bearings can actually prevent the bearings from fully seating when the main caps are all bolted down. At the very least, it will affect your oil clearance measurements. Many people overlook this. It's like Russian roulette. It won't happen every time you fail to do this step, but in my opinion, you should always do this whenever you're installing a crank. You want all of the bearings bone dry and tightly seated against the surface of the block so that when you install the crank and torque it down, they'll etch themselves tightly in place on the first heat cycle. The bearings that go in the block have a 180-degree oil groove around their faces to feed the oil to the crankshaft and ultimately to the rods. The faces of the bearings on the block side have relief holes for the main oil galleries that feed that groove, and only the number 1 journal on the block has provisions for an oil return on the other side. If for some reason only one of your non-thrust bearings has a hole in it, it goes on number 1 to feed your oil pump and balance shaft. To install either set of bearings, you rid all the parts of foreign material, line up the tanks with the grooves, make sure the bearings seat fully, and that all of your oil holes are correctly lined up where they need to be. If you know to look for this and what the oil holes do, it's really hard to get it wrong. Even though I've cleaned the crank, I'm cleaning it again. When you're checking your oil clearances, you want to put the crank in dry. Don't turn the crank on dry bearings. You just want to set it in there so that the oil holes are slightly off center. Plastigauge is what the factory service manual says to use for this. Buy it at your local parts store. They have it. It's cheap. The factory oil clearance specification on a 4G63 dictates that you should be using the red plastigauge for your mains and rods. It's easy to use. You just cut a piece long enough to fit between the fillets on the crank, then install the caps and torque the mains down using the factory service manual specified procedure. I've covered that in another video, so I won't be making this one any longer than it needs to be, and I'm being a little sloppy anyway for whatever reason I can't explain. When you're installing your bolts, it's important to oil not only the threads of the bolts, but the mating surface underneath the head of the bolt as well. If you have washers because you're using main studs, you should lubricate both sides of those as well before installing the nuts. Always run the bolts down by hand and snug them first. You should have already cleaned the threads, but if there's any trash in the bolt holes or if there's damage on the threads, you'll only feel it without causing damage when doing this by hand. There should be 0 snags or tight spots. Torque the main bolts specifically to the torque recommended by the bolt's manufacturer. If they're factory bolts like these, use the torque specified in the factory service manual. In my case, it's 49 foot-pounds. Of course. Sorry about that. Back to torquing. Be very careful not to turn the crankshaft at this stage of the dry assembly, or else you'll be cleaning this up and doing it all over again. After it's torqued, just take it all back apart again and check the mains using the guide printed on the plastigauge packaging. That's dead on 3/1000ths. I say dead on, but that's just the measurement. This is 1/1000th over spec, but it's still 1/1000th short of the service limit. While it's better to hit spec on your average street-driven daily driver, this engine doesn't exactly conform to having a normal factory oil system, and I view this wide spec on the mains as a good thing. Since this is a no oil squirter, no balance shaft, non-turbo block, it's missing 7 oil galleries, and there's a lot of oil volume being pumped that would appreciate having somewhere else to leak out of. I intend to set my mains and rods up a little bit on the looser side of things within the service limit. I'm not aiming for 100,000 miles of wear on this build. I expect it to give up long before then, but slightly increasing the oil clearances is one of my means of dealing with it for now. You can scrape off the plastigauge using your fingernail, but I like to use an electronics tool called a spudger for this because it's made of nylon. It's softer than the parts, but it's harder than a thumbnail, and it's a little less clumsy. Once you've got the last of the plastigauge removed, you have to clean everything all over again. Write down all of your measurements for reference. I got 3/1000ths on every last one of my mains. Never mind that I misspelled plastigage, all the right letters are there. The order doesn't really matter. These aren't the droids you're looking for. There's the factory spec that Mitsubishi says to use. Now where was I? Oh yeah, you have to clean everything all over again. Doing this job right is very repetitive. My favorite cleaning solutions are denatured alcohol and this acetone-based parts cleaner that you've seen in plenty of my other videos. I use them because it cuts through film layers and leaves no residue. This is not the assembly lube I want. This is the assembly lube I have. I'm just glad that I'm finally able to put a crank in this block. So here we go cleaning the caps again. Everything's getting the coffee filter and compressed air treatment until it comes out spotlessly clean. Even if this repetitive cleaning seems like overkill, it's all in an attempt to minimize foreign material during assembly, and every little bit helps. Lube and install the main caps and use the same torque procedure you used in your dry assembly for the bolts that you have. It's important that you always use the recommended lubricant and torque. Some are more slippery than others and can affect the bolt stretch during the torquing procedure. The purpose of a torque procedure is not to just put the right amount of load on the bolts, but it's to ensure uniform bolt stretch. Failing to do so can result in catastrophic failure of the rotating assembly. If you use moly lube on factory bolts, you'll overstretch them. If you use oil on ARP studs, then you won't achieve the proper bolt stretch. That's why the lubricant selection here is so important. If you've done everything properly, when you're finished you should be able to spin the crank with 2 fingers. If you can't, take it apart and figure out why not. Another measurement you need to check is the thrust clearance. I covered this in Blueprint 102. First up we have the feeler gauge method. You shove the crank to one side using a small pry bar and you see how big of a feeler gauge you can fit between the thrust washer and the crank. I find this tedious even though it's really easy. Feeler gauges are crude and I have much more expensive tools that will do the exact same thing. So there you have it. 0.006. 6.5 if I really mash on it in both directions. I'm going to be pounding on this thing and I want it to be on the wider side of spec. So how does the old saying go? It's better to be pissed off than to... Oh, never mind. I've got a crusty set of 30 over non-turbo pistons pressed onto 6-bolt rods that I intend to keep using. Before I tore into this job, I was told that they will all be out of spec and that this is intentional. I'm not expecting to find anything different. Everything else I've been told so far has been true. Pay attention to all the markings on the pistons and know what they mean. There's also an arrow which points to the timing side of the block. Pay close attention to that thing. Just like with measuring the crank and the rod journals, you start by cleaning the micrometers and checking or setting your 0 point. You want to measure about 5/16 of an inch up the way of the piston skirt, even with the bottom of the piston on the pin sides. That's supposed to be the wide spot right above where the piston wears. I'm deviating slightly from the service manual procedure here. Rather than zeroing my bore gauge for the tight spec and taking my measurements, I'm locking the micrometer and zeroing the dial bore gauge to the piston measurement. So any measurement I take anywhere in the bore is the piston to cylinder wall clearance. It's cheating and it's not perfect because of the type of gauge that I have, but I do this. I'll explain it better when it's more important. For now, I'm going to take measurements and write down just what the gauge says. You're not only supposed to get thrust measurements here, you also take measurements parallel to the crank. This helps you to determine if there's egg-shaped wear in the cylinder bores. Even though the piston measurement is arbitrary in relation, it doesn't change the accuracy of this test because the dial bore gauge is still zeroed to a single measurement, the same one we took on the other side. So any variation in relation to the Y measurement will be very easy to spot as a different number on the gauge face. As you're working, write everything down. If you don't write it down, it never happened. Repeat these measurements at 3 depths in every bore, bottom, top, and middle. Note any variation in the cylinder bore's roundness and taper. A little bit of taper doesn't hurt. In some cases it can actually help the rings seal better because it keeps them moving. But don't attempt to create this situation without doing your research first. Everything we're finding here is incidental, not intentional. It's a whole lot of measuring, zeroing, writing, and measuring some more, but what you gain from this is valuable information about where and what it would take to correct it. You can sometimes get away with a few of these variables being out of spec and still make good compression, but on a new set of pistons or rings, if the bore isn't round, you're losing compression and horsepower because the new rings are never going to seal right. Don't change your rings out if you're not resurfacing the bores. I'm keeping the old pistons and rings and bores exactly the way they are because right before this thing came apart I did a compression test and got between 165 and 175 pounds on every cylinder. My piston spec is 0.75 millimeters or 30,000ths overbore. They're generic non-turbo 9-to-1 compression gallant pistons and non-turbo rings. Here's the bore specs for a factory block. And you could just throw that right out the window in my case. This thing's been Ron Jeremy'd already, so mine's way, way out of spec. But what is important to note in my case is the piston to cylinder wall clearance. These numbers look terrifying compared to spec. Never fear, they're just backwards because of my dial bore gauge. All I have to do is subtract 1/100 of an inch from all of them and I've got my clearances. Anybody can make change for $1. So what we've got here is number 1 and number 3 are egged way past the limit. Number 1 is egged horizontally at the bottom and vertically at the top. Number 2 is the straightest, but its clearances are right at the end of spec. Number 4 is at the limit for taper. Anyone with a head on their shoulders would junk this block and start over, or punch a new set of holes and get a new set of pistons to correct this, because at 30 overbore, there's no room for machining to take out the imperfections that this block already has. So the egg is out by 10 thousandths at the top of number 1. You'd have to cut it deeper to fix it. I'm nuts. I'm going to put this worn out beast back together the way it is. But before I do all that, I want to take a closer look at the rings. You got 5 rings to deal with, number 1 and number 2 compression rings, and the oil ring assembly, which is an oil ring and a top and a bottom rail. There are 2 gaps to verify for the rings. One is the gap inside the ring grooves, and the other is the gap between the ends of the rings. You don't need to check side clearance on the oil rings, just the compression rings. The gaps accommodate thermal expansion, so how an engine's used determines how to gap the rings. You check the gaps for both measurements with feeler gauges. When you're disassembling your pistons, always use piston ring pliers on the compression rings. Pay close attention to the shape and the color of the rings and any markings that help you determine their orientation. Some may have stamped markings on them to indicate which way is up. Others will be burnt on one side and shiny on the other. Different types of rings have different shapes, and there's a diagram in the service manual about all that. Sometimes they're beveled or grooved. Give them all a thorough inspection to ensure they're not cracked or bent and that no binding has occurred. Move on. To find the side clearance in the grooves, take the ring off of the piston. Clean out the grooves and run the ring around the groove while you check it with the feeler gauge. You sort of need 3 hands to do this, and it takes patience until you get a feel for it. There's 40 measurements to have to take here, so it still takes patience once you do get a feel for it, but this one was pretty easy with the 3/1000ths, and I could get the 4/1000ths in the groove, but it was really too tight. The other measurement you need to take is the ring gap. It's a simple process, really. You get a piston, your feeler gauges, the ring, and pay the hole in the block a visit. It's hard to get lights, camera angles, rings, tools, my hands, and my line of sight down in these bores all at the same time, but the process of checking the gap is really easy. You start the ring into the bore by hand, and you use a piston to shove it down level in the bore. Then you take a feeler gauge and probe the gap until you get the largest one that will fit. If it moves the ring when it goes in, recenter the ring and make sure you didn't go too big on the feeler gauge. Once you're satisfied, write the measurements down. This is actually encouraging so far. Let's check out the next compression ring. Again, always use ring pliers on these compression rings. The number 2 compression ring is where you're most likely going to find markings indicating its orientation. This one's actually stamped top right there on that left edge there, but often you'll just find a dimple. Do the same kind of inspection for deformities and cracking as you did with the first ring. Carefully scrape off any of the carbon if you find it. In fact, you're supposed to clean the carbon out of the piston grooves before you even do these tests. These pistons came out really clean with just mineral spirits, but I can't take that for granted. It's the principle here. You're supposed to scrape the grooves out, and I'm shooting a video about this. Come on, Jaffer, I told you I'm being sloppy. I don't know what it is about this Hyundai, but you can take the oil rings off by hand. Just be smart about it. Don't bend them. Start on an edge and take it over the top of the piston. The rest will follow it. Find the gap in the oil ring and make sure it looks healthy. It's really easy to figure out which way these things go because of how they wear. Just put them down in the right order on the workbench so you don't mix them up. An acetone-based cleaner and a nylon brush should dislodge any carbon that's left on the pistons without scratching them up. You can see how clean it was to start with just from that quick mineral spirits and air bath. I should really be wearing gloves for this. But if there's funk that you can't remove like that, another old school tried and true means of cleaning out the grooves is to break an old compression ring and run the edge around the groove to scrape out any funk. The reason you want to use ring pliers on the top 2 rings is because they're extremely brittle and prone to deformation and breakage. One mistake and it's trash. Even generic $4 ring pliers are enough to prevent it. Did you see how easy that snapped? It just shattered. This is why they make piston ring pliers. The oil rings are much more resilient, but you should still be gentle. They also make pliers that can clean out the ring grooves for you. And although they do a great job, most people that own those things still break off a ring and scrape it by hand. This looks fantastic. The number 2 ring is thicker, and you can just as easily break off another one of your other spare rings. You only wish you had those ring groove pliers if you don't have any spare rings. Doing this manually is pretty much beginner level hand-eye coordination, and the results are always fantastic. Just be careful not to scratch up the piston. Look at these results. While the acetone dries up, let's go measure the number 2 ring gap. The number 2 gap spec is about 18 to 24 thousandths on a turbo DSM. You use the same technique for this and all 15 of the other rings that you need to measure. I'm pretty optimistic now. That's in spec too. I hope to see more of that, and only time will tell. Now that the grooves are clean, measuring ring side clearance is exactly the same process as the method I demonstrated earlier. And the top 2 compression rings of a turbo DSM actually use the exact same spec and service limits for their side clearances, which is convenient. For the ring gaps, it's a whole different story. If you can't fit the 3 thousandths in the groove, but the ring turns freely, then it's in spec. As long as you can't fit the 4 thousandths, then it's still got some life left in it. If the ring is hard to turn, then it's too tight. This is easy stuff. It's just a process that you should follow to prevent having to do this job twice. I'm going to super warp speed once we get to the number 2, 3, and 4, but I'm still going to show the work being done. Sorry about all this info coming at you with the speed and frequency of helicopter blades. I'm doing my best to explain what's going on, and some of it I wish I could go into more detail about. Doing this in a single video is difficult because of how many steps are involved and how much ground we need to cover. It's 10 pages of the service manual. Now let's check out the oil ring gaps. Some people put a ring on a piston and use it as a stopper so that it stops even and flush at the top of the block. If you insert the piston deep enough using the full length of the piston skirts, then it will be level in the bore. My block has enough defects in the bores that the middle is actually the most uniform part of it. The tricky thing about these is not only keeping them in the bores while you're measuring them because they're so loose, but the fact that the service limit spec on these is bigger than your average set of feeler gauges. To work around this, double or triple up however many are necessary to get the right measurement. Though these are the least critical of the set, you'll probably spend the most time fighting these because they like to move around. You want to be calculated in all of your movements with the rings. Don't ever drop the rings on the floor, try not to stress them by holding them tightly or setting things on them, and don't lose track of which one you have or which way is up. So here we've got a 42 and a 45 thousandths. Both of those are past the service limits by a few thousandths. Now that we've covered one piston, I'm going to take the rest of the rings off and do the rest of my measurements. Finish cleaning up the pistons and rings, install bearings, check my rod oil clearances and rod gaps to complete the dry assembly, and make any changes that are necessary. Then I'm going to do a final cleanup and prep for assembly. Hang out because in about 12 minutes I'm going to have an installed rotating assembly. That's not a spoiler, that's what we set out to do here. As I move through these measurements, I'm surprised to find the number 1 and number 2 compression rings are in spec. I was expecting to find them all near the service limits based on what I was told at least, but only the number 1 compression ring on cylinder number 1 was wide. The rest don't look like that. The rest appear to be on the looser side of spec, but all of them are still in spec so far. At least the top rings are anyway. The bottom compression rings are gapped wider than the tops, just the way I like them, but the number 2 rings have plenty of room left to wear before hitting their service limits. I'm not the least bit surprised by the loose oil rings because these pistons are a little bit on the slappy side. Wide piston to cylinder wall clearances. They're all between 5 and 7 thousandths, past the service limit with the exception of only one ring in number 3 that's right at it. I'm okay with this because the compression rings are set up loose and there's a little bit of sloppiness. I don't believe it's affecting oil delivery to the bores in the least. But when we get to number 4, the compression ring gaps look a little bit weird. The number 2 compression ring gap is 5 thousandths tighter than factory spec. The specs written on the board in black aren't relevant here. Those are just side clearance and service limit specs for the A measurements. We're talking about the B measurements here. The bold dimensions on the bottom are the service limits for the compression rings and the oil rings. What you see on the screen right now in green are the ring gap specifications for the top and bottom compression rings. That's the B measurements, OE spec, for a factory fresh engine. The bottom compression ring on number 4, after all this engine's been through, is somehow 5 thousandths too tight. I'm glad it never touched down because there would be nothing left of that piston right now. But I'll be turning up the boost and throwing quite a bit more at this after the rebuild, so it would be wise for me to correct that. I need a little break from the rings, and they can wait for a bit because I'm not done inspecting all the other measurements that I'm after. When you're doing a dry assembly and your pistons are already assembled, it's best to get your rod bearing and oil clearances straight prior to installing the rings. In order to take those measurements, once again, everything has to be spotlessly clean. My process on all bearing surfaces is to clean it with denatured alcohol and compressed air. Just like with the mains, you need to clean the oil off the new rod bearings using the exact same process. This helps ensure that no foreign material becomes lodged between the bearing and the part. Since these parts are oil free, I'm putting a drop of oil on each rod bolt to soak in. Clean up the nuts for the rod bolts and lay them out in order. This takes a while, but fortunately all the rod bearings are the same, so there's a bit less to pay attention to. You can just do the autopilot thing here. This isn't exciting enough. Prepare yourselves for super warp speed. Now for a quick blast of air to blow out any dust, and we'll start prepping for the plastigauge. Cut strips for the rods that are long enough to rest between the fillets. Get your oil can, torque wrench, breaker bar, 14mm socket, and piston ready. Pay attention to your markings and cap orientation and carefully install the piston without contaminating the surface or disturbing the plastigauge. Oil the nuts with the recommended lubricant for your bolts. Run them down by hand. If you're using factory rod bolts, the torque load for those is 38 foot-pounds with engine oil. I torque in stages, gradually setting both nuts evenly. I aim for about 22 pounds as my halfway mark, and then torque to spec. Orient the wrench perpendicular to the crank so that it doesn't turn the crank. The plastigauge smashes to different widths depending on how much clearance there is with the bearing and the journal. The tighter the gap, the bigger the squish. It's just like the mains we looked at. When we looked at the packaging, it looks like that we've got 3/1000ths of an inch here. That's a little looser than I want to have it for a rod bearing. It's actually a full thousandths out of spec. Factory spec for rod bearings clearance is 8/10,000ths to 20/10,000ths with a service limit of 4/1000ths. We've got 30 here. That's a little big. Let's move on. Same process. Get your clean stuff, stuff it in there, lube it, honk it down tight, and then I go and do exactly what I just said not to do, torquing parallel to the crank. The plastigauge doesn't begin to squish until you've got both caps butting flush up against the rods, and you saw me turn it. I didn't have the bolts tight yet, so I got lucky. There it is, 2/1000ths, dead on all the way across. That's really more around where I'd like to see the measurements. Next we'll do number 4. On a 6 bolt, it's a little tricky working around the suitcase handles. This is the best way I can figure out how to orient it. You need to be careful not to put the plastigauge down in a location where it will smash into the tiny hole that's drilled through the bearing, or it'll disrupt your results. It makes it harder to read taper if this happens to you. Looks here like 2/1000ths is too big and 3/1000ths is too small, right in the middle. We'll call that 25/10,000ths. And finally number 1. I could live with 25/10,000ths. It's a little bit loose, but this car's oil system can deal with that better than it could being tighter. The important thing is that they're all even. Speaking of which, this one's also 25/10,000ths. So number 1 and number 4 are 25/10,000ths. Number 3 is my tightest, and number 2 is my loosest. They're not all even like I wanted them, but I've got an old trick that sometimes works to correct it. You take your wide bearing and your tight bearing and you swap them. Most people find there's a little variation in thickness between most brand new bearings, at least enough to create an anomaly in your measurements. Frequently there's also a little bit of variation from one to the next, even in a freshly machined part. This can work against you or in your favor, but usually in your favor. It's always worth a shot if this happens in your measurements, because it helps you to put together a more uniform oil system. If one's looser than the rest, it will leak more oil, at least more than the rest. If it's really loose and out of shape, it will change how the oil film layer behaves on that bearing. But when you swap them, and I told you this was tedious, you have to once again completely clean all of the parts all over again. The crank, the bearings, the backs of the bearings, the rods, and the caps. And then check them each time you make changes with the plastigauge to see if it made a difference. If this is something you think you might need to do, stock up on plastigauge. I ran out of plastigauge and had to go get more. There's just enough in a single pack of this to do all your mains and your rod clearances, and then have enough left over to drop a piece on the floor and screw up one attempt. Some auto parts stores sell this stuff in single packs in whatever color you want. The colors represent different size ranges. But some vendors make you buy them in 2 packs like this for 3 times as much money. It's the difference between $1 and $5 for a 2-pack that you'll only ever use half of. I really don't need the green stuff. I never set up anything that tight. There's also a blue kind available that measures between 4 and 9/1000ths of an inch, and nobody with a 4G63 needs to use it for anything. The red stuff gives you the best info for most DSMs. The proof is in the pudding. Let's see where this lines up. It's bigger than the 3/1000th mark, meaning it's tighter, and it's smaller than the 2/1000th mark, meaning it's bigger. That puts me right in the middle between 2 and 3/1000ths, just like the rod bearings on number 1 and number 4. I like seeing this because it's a good sign of what I'm hoping to find on number 3. So far the trick's working great. Taking the time to do this can prevent you from needing machine work to correct minor inconsistencies, or having to buy different bearing sets. Don't expect for John Q. Mechanic to do this for your build if the numbers fall within spec. This is a level of detail you will only get working on your own equipment. Number 3 is ready for inspection, and let's see where we are. Bigger than 3, bigger than 3. Smaller than 2, smaller than 2. That's right in the middle. That's exactly what I wanted to see. That means that all 5 of the mains are 0.003, and all 4 of the rods are 2.5 She's even. She's set up on the loose side of things within the service limits of my new crank. And after one final cleaning, I'm ready to start installing pistons and rods in this thing. I already cleaned up the number 1 piston grooves and rings, but number 2, 3, and 4 need the same treatment. I need to finish my ring measurements, and it's true that it's my least favorite part of a build, but it's one of the most critical steps, so I really need to do it. I mentioned before that tight rings can destroy pistons, and what I mean by that is if the ring binds, it seizes inside the bore and breaks the piston off at the ring groove. I don't need to explain to you why this is bad, but I will say that the piston won't be the only casualty when that happens. It will take out the block, crank, and rods as well. So no matter how much you don't enjoy doing this, trudging through it gives peace of mind knowing you won't ever have that happen to you. When you're setting up your rings, think about how your car is used and vary your gaps accordingly. Cars operating within the factory power output range can benefit from being set up on the tighter side of spec. If you've got a 300 shot of nitrous hitting this thing every weekend, you probably want to double the wide spec for starters or go clear past the ring service limits. There's often a chart included with the rings or the piston and ring sets that you can refer to for guidance. But in all cases, you want the top of the ring gap narrower than the one below it, or else something called ring flutter may occur. Okay, that was the chair I was sitting on. It was the chair. I'm serious. That's my story and I'm sticking to it. Had that been my own gas, I would have edited it out just like I always do. I have to do that quite a bit actually. I confess, it happens continuously every time the record light turns on. I'm fine once it stops. I don't know what it is. But where were we? Oh yeah, ring flutter. If the second ring is tighter than the first, then when the boom happens, pressure is trapped between them. It backfires through the number 1 ring back into the combustion chamber, and the number 1 ring basically doesn't seal during the combustion stroke. If you set the number 2 piston ring several thousandths wider than the number 1, you avoid this condition. It allows more blow-by, but it's worth it if your rings seal better. Of course, all of what I was referencing with that discussion is the B measurements that we were working on earlier. We're finishing up measuring the ring side clearances now, which are the A measurements. What you'll notice at first glance is that the top compression ring is about twice what the bottom ring specs out at. Only with one exception as always, on number 4. The service limits in black on the side are for the A measurements, and 5 out of 8 of those measurements are in spec. The other 3 are just short of or right at the service limit. If these rings go, my fix for this car will be a new block because of the work involved for a new set. 7 out of 8 of the compression rings are in spec. Number 1 on number 1 is wide. It's also my low compression piston, so I'm not going to grind the number 2 ring any wider on number 1. I'm going to gamble on thermal expansion closing the upper gap tighter and leaving that one alone. The top rings swell more than the bottom ones with heat, but that one's on the edge of me wanting to do something about it. So now that we're ready to install rods and pistons, there's only a little bit left to do. You probably saw me install all the rings without explanation a minute ago, and there's a good reason for it. It's harder to see what I'm doing in the video than it is to see it in a diagram. You got 5 rings to deal with and you know which ones they are by now. There's a top one and a bottom one for each kind, excluding the corrugated looking oil ring. If you hold the piston so that the arrow points to the left and treat it as a dividing line, the top rings all go on the top, the bottom rings all go on the bottom. Each kind of top and bottom rings are oriented opposite of one another, and the oil ring lines up with the bottom compression ring. So the number 1 compression ring always gets 130, number 2 in the oil ring gets 730, the top oil side rail gets 1030, and the bottom one gets 430. Top rings on top, bottom rings on the bottom. If you're using some far out piston with 6 rings, refer to their instructions over mine. You don't want the gaps on the rings to line up on the thrust surface sides or the sides of the bores if you expect them to seal. Now it's time to install these puppies. You'll need ring compressors in order to do this. I've got an old Ampro set that's already had its jinx removed. This is what the Harbor Freight version of it looks like, but I refuse to use that thing because I don't know it. It's exactly the same tool, it just costs a quarter as much. I'll explain the jinx later. I use ATF to lubricate the cylinder bores and the pistons. The reason I like to use ATF is because it's a dynamite cleaner and rust preventer, and it's also a mild lubricant. I don't like using engine oil on street strip cars because it has a tendency to glaze the bores, and that changes the break-in process. If you want your rings to bed slowly with a 50 or 100 mile break-in, then fine, use engine oil. If you're going to heat cycle it, change oil and go, then use ATF. Now it's time to clean out the block. I use ATF and coffee filters for this too. It's nice that it's a bright contrasty red because it's easy to see on a white coffee filter. You wipe out the bores until the filters come out nothing but red. You should blow it out when you're done. You really don't want fibers of any kind inside your engine, but these aren't going to hurt it in small quantities. I clean the crank journals with an acetone based cleaner and blast them clean with compressed air. I use Aerocroil on the wrist pins. It's enough. It will be quickly displaced with engine oil on first startup, and in the meantime it'll repel moisture, penetrate deeply into the pin bores of the piston, and it will provide all the lubrication necessary until they do see oil. This product doesn't have the load rating that engine oil does, but this is a product that's used to unseize pistons and immediately return an engine back into service, so it's not going to bind. Look, there's 4 rod caps smiling at you. I think they like their new bearings. Put a 3/16 inch to a 1/4 inch bead of assembly lube on all of your rod caps so that they're ready to go. Once you start this, you're rolling. Don't leave them sitting around. Blow any foreign material off the rod bearing surfaces, check the ring clock, and then make sure nothing's shifted. Then douse the rings and the skirts with ATF. Wipe out your ring compressor to ensure it's clean. It's at this stage where you take your gooey ATF soaked piston and squish it with the ring compressor. The band overlaps, and you want to make sure to keep that straight. Put the 2 silver bands that go around the tool right in the middle of the piston. Put it on the last click, apply assembly lube to the rod bearing, and go visit your block. Once you've got the piston in the bore, before you do anything else, you have to take the wooden hammer handle that you're going to use to tap the piston into the bore with and mash it across the top of the ring compressor to make sure the tool is perfectly flat and flush with the deck of the block. Then tappity tap it home. Now we flip the block, grab the caps and the nuts, and do our final torque. You install the caps with the tang side of the bearings on the same side. Don't put them on opposite sides. Tangs go together. Before you snug the nuts, oil them with a recommended lubricant. You know the drill here. 1 down, 3 to go. The reason I said the jinx was removed is because anyone who builds an engine inevitably bends a ring installing them. It's just how it goes. You're guaranteed to do it if you don't have ring compressors perfectly flat and flush against the block. You have to do the hammer handle thing and mash it, tap it, and hold it down flush. If any gap develops in the tool, inevitably a ring will pop out and snag the edge of the bore, destroying them immediately as it's driven in. This old set of ring compressors did that on the first build in someone else's hands. It didn't like wrapping around a tiny little 1.5 liter Honda piston, and one of my friends bent a ring installing it. Since that day, this thing's built a half dozen engines and has never once bent a ring in my hands. That's why I won't use anything else. It's just a growing pain. Everyone who builds engines messes up at least 1 ring in a lifetime. There are also some really expensive ring compressor pliers with a band or a pair of tongue-like cups on the end. I can't stand those things. Not on a DSM anyway. I don't know what it is about them, but I can never get it to compress the rings as well as this old low-end Ampro ring compressor. It's as if they don't make the bands quite the right size. One's a little too big and the next one smaller is a little too small. It's also hard to keep it flat against the block. The kind that I have is always just right. You grab the Allen looking key, you honk it down until it honks no more, and then you install it. And if you use it correctly, you won't ever have any problems with any sized piston. You just have to mash with a hammer handle, tap it, and hold it down tight. Oh wait. I was going to fix a ring, remember? The tight one on number 4. For this thing, I just take a couple of blocks of wood and carve out some quality time with my bench vise. I use the blocks of wood to secure the ring without damaging it, and to take the load off the end of the ring. I do this by putting the tip of the ring that I'm filing flush with the wood blocks, and then run a fine file over the end. There are tools designed to do this with precision, and I'll show you that thing some other time. This is how to do it right without it. Even a fine file is too rough. So once I'm just barely short of the gap I'm aiming for, I clean up the last pass with fine emery cloth. You don't want to round corners or edges here, but you don't want any burrs and you want it to be smooth. Do one last check to ensure it's the right size, and then we're going back to dropping in number 4. I apologize for my sloppiness today. I should have done this a long time ago, at least I remembered. Here's one last close-up of the piston install process. Now that the rotating assembly is installed, I only have one last unfinished measurement, the rod gaps. This is something you should really do prior to disassembly, and then do it again after you put it back together. You find which feeler gauge fits into the side clearances between the rod and the crank, check it against its spec, and I did a video on that already. There you have it. That's everything you need to do in order to install your 4G63 rotating assembly. If you followed a guide and everything's in spec and you did every measurement, then technically your engine is blueprinted even if you wrote nothing down. I recommend writing it all down so that you have a point of reference later and so that you know every detail is verified. So these were my results. I didn't bother taking measurements of the original crank and rod clearances except to discover that every journal on it was turned 10,000ths over and it had oversized bearings. I replaced the crank, bearings, and filed only one ring gap, putting it all back together just like it was. What's in blue is all I ended up changing. I like those oil clearances since I don't have balance shafts or oil squirters, and I'm happy with the rest of my oil system modifications, but there's a reference in case you ever wondered what this thing was made of. I'm glad you stayed through the whole 6-bolt journey with me, and I hope your engine works at least as good as... Wait, this is the Hyundai. I'm not sure if that would be really a compliment.